So hi, I'm Jin Mainprice. I'm going to talk about how we can use numerical optimization to solve motion planning problems with narrow passages. So if we look at how humans share space, especially in dynamic situations, we can see that they handle changes in geometry at a very high rate while remaining somewhat optimal in the way they move. And we try to formalize this idea in a robotics framework about 2 years ago. So we modeled the geometry using three-dimensional occupancy grids, and we were able to handle this using a model predictive control fashion trajectory optimization at about 10 Hertz. And then we reduced this geometry in order to handle it at about 100 Hertz using more local control, and combining the two into interlocking feedback loops. And one of the bottlenecks of this approach is the trajectory optimization itself. So we have constraints in the form of joint limits and collision constraints, and we have objectives in the form of remaining close to a standard configuration and joint space and task space smoothness terms, like limiting accelerations along the trajectory, and a terminal potential. And the way that nonlinear numerical optimizer would work is by computing Lagrange multipliers and generating an unconstrained proxy for this problem. Once we have this, we use a Newton method to solve at a very high rate this problem. So we compute the gradient of the objective, and then we compute the Hessian, or an approximation of the Hessian of this objective, and multiply this gradient by the inverse of this Hessian term. So one of the key difficulties in this approach is that the potential around the obstacles is highly warped and leads to highly noisy estimation of the gradients and of the Hessian terms. So what we propose in this work is to formalize the problem using Romanian geometry and to kind of study what is the impact on the numerical optimizer for narrow passage problems. So how can we do this? So we can take a Euclidean version of the workspace and map it to a workspace geometry map, where the geodesics for around each of the obstacles are going to be well defined. Then we can pull back this geometry using the Jacobian of the map, which will generate a Riemannian manifold which has the desired properties. And in the second phase, we can define a geodesic flow, which is going to tell us for any point in space what is the direction of the shortest path to the goal. So we can define this geodesic flow by a diffusion process which is going to integrate the Laplace equation over time. So we have our source here, and we diffuse our potential over time by integrating the Laplace operator of that potential. And so this leads us at convergence to a potential which is harmonic and has only one local maxima or minima, which is actually the goal here. So the potential must be solved in order to get the vector field, which are these white arrows here. So how can we use these insights in an interior point method? So first, we define constraint terms, which are, so this is just the typical sign distance field. And then we define constraints which so these have to do with collisions, and then we define constraints which have to do with achieving the goal. We define 3 of them, and then we compare them in our experiments. So we have a typical Euclidean goal constraint, then we have a natural goal constraint, and then we have our geodesic, which comes from this diffusion process. And as I said, we are going to see how the 3 of them actually outperform or perform each other. Then we have objective terms which have to do with squared acceleration along the trajectory, a geodesic term, and a geodesic flow term, which is the agreement between the direction of motion at any time and the geodesic flow itself. And then a joint postural term. So we include them, all of these things, in our interior point method framework, and we compare those on 3 different examples. So a planar and 2 3-dimensional examples where we have 6 degrees of freedom, and we compute a goal region of about 30 goal points, and we watch what are the success rates of using different tuning of the objective terms, and we find that the ones that use the Romanian geometry lead to higher success rate. So obstacle-based Romanian geometry is defined in this work using a pullback metric for the metric itself, and using diffusion for the geodesic term. And we find that considering Romanian geometry actually leads to more effective motion planning, and both the geodesic term and the attractor matter. And finally, that the challenges are, what are the impact of this for sampling-based motion planning, which has been studied for the last 30 years, and how can we use more effectively the geodesic term. So I would like to thank all my past and present collaborators, and I will take any questions.